I am thrilled to be here. And as Matt said, I'm going to be talking about how to specify RL objectives. This is work that is uh, in a paper that you can get on through the QR code and will be on archive soon that I'm working with James McGlashan on. But it draws heavily from work from several past papers. And I'll just make sure to mention Peter Stone is heavily involved in some of this past work, as well as Serena Booth. Also, let me set some expectations here. This is not a talk about how to make your RL algorithms work better by changing the objective. It's about how to specify the task that you actually want solved in a way that is aligned with your own preferences. So this is very much in line with the way it's represented in Sutton and Bardo. Okay, so let me launch into this. Actually, one more thing. I highly encourage clarifying questions, but let's save other types of questions for the end because I have a lot of content here. I'm going to talk about aligned RL objectives and what I mean by that, motivate them a little bit. And then I'm going to talk about ways that you can find misalignment in a reward function or a RL objective more generally. And then 3 methods that commonly cause misalignment: shaping, trial and error, reward design, and discounting. And then I'll talk about all of those are ways to find problems. And then the 6th part will be trying to take this like a positive perspective and talk about ways we might approach designing aligned reward functions. And then I'll end with some future work. All right, what do I mean by aligned RL objectives? So to explain that, let me just review some notation. We have a reward function over here, R. It takes the state and the state at time t, the action taken in that state, and then the next state. This is just the most expressive common form of the reward function, and it outputs a scalar value. And this reward is going to be summed over a trajectory, which is tau on the left side, and there may be some discounting. And for the first half or so of the talk, I'm going to assume this gamma discount factor is 1. So basically, there's no discounting until I come to discounting specifically in the talk. So this discounted sum of reward adds up to what we call return. And this can be expressed as via this function g over the trajectory tau. This is an RL talk, but I just want to link this briefly to other fields. Motion planning, control theory, evolutionary algorithms all have related terms. And so the content of this talk, for the most part, can be ported over to work in these fields as well. All right, so we talked about reward and return. Expected return is just the mathematical expectation of return given a policy pi that creates a distribution over trajectories. So this is expressed as j of pi, and this is the overarching evaluative metric for a policy. And this expectation is an abbreviation. I'm happy to go into what exactly it is. There's a start state distribution as well. Okay, so given expected return, RL is attempting to find a behavior policy pi that maximizes expected return. Or at least policy improvement more specifically. But usually that's what we mean when we say RL. Before I go into this further, I just want to note there are alternatives to reinforcement learning. If you have a sequential decision-making problem and you want a policy for it, you could try other approaches, such as learning from demonstrations, imitation learning, or learning from preferences, which is often called RLHF. But even if you do these methods, there are categories of these methods that learn an intermediate reward function and then do RL on that reward function. And for those versions of these methods, the content of this talk is appropriate too, because you can, at least some of the content is, because you can assess the alignment of those reward functions. Okay, getting to the definition. What do I mean by an aligned RL objective? I apologize for the block of text here, but let me step through it. I'll illustrate what I mean in a second. But an RL objective, which for the context of this talk is a reward function plus some discounting scheme, create a preference ordering over possible trajectories by this return function, G, and probability distributions over trajectories by the expected return. these trajectories can be simplified to only the outcomes that matter to make them more human readable. So for instance, if you're playing like a board game, you might simplify a trajectory to just whether it ends up winning or losing. Or if you're trying to get to a goal as fast as possible, you might simplify the trajectory to the time that it took to reach the goal, or the number of time steps. And then given these simplified trajectories and distributions over trajectories, we're going to assume that humans also have such an ordering. And so my definition that I'm going to use for this talk, which is not a new definition, of a perfectly aligned RL objective is one that creates an ordering over outcome distributions or trajectory distributions that matches that of the human stakeholder. I am not going to talk about the very important problem of social choice and how to handle when there's multiple stakeholders that don't have the same preferences. That's very important, but out of scope. Okay, let me illustrate. So let's assume we're doing autonomous driving, and this is an extremely simplified autonomous driving task where there are only 3 possible trajectories. And those 3 trajectories are tau success, meaning that the car successfully gets to the goal, tau idle, it safely doesn't drive, and tau crash, where it drives halfway and then it has a crash. I hope that we will all agree that these are ordered from best to worst, top to bottom. And let's just say there's an RL objective that assigns the following return for these 3 trajectories. In this highly simplified task with only 3 possible trajectories, this would be an aligned RL objective because it orders by return these three trajectories the same way that humans would. Okay, now let's add some domain stochasticity. And let's say that there's a 4th possibility, which is a lottery over successfully driving or having a crash. So note, this is a lot like real driving. We try to succeed, but sometimes there's a crash. But let's say this is a 90% probability of success, 10% of crash. Again, I hope we will all agree that these are ordered by correctly by human ordering, where we would rather not drive than drive with a 10% probability of a crash. However, because we have the expected return for these other trajectories and the probabilities in this lottery, we can calculate the expected return for this lottery is 4. So this is a misaligned RL objective now because the 4 is higher than the 0. So the expected return is ordering the lottery as better than not driving. I'm going to stay at a kind of a mostly practical level in this talk, but for a very deep dive and an equivalent theoretical treatment of this definition of alignment, I highly recommend reading Mike Bowling's paper from ICML last year, Settling the Reward Hypothesis. Okay, so let's kind of get some more intuition in a different way. I'm going to ask everybody to mentally, or if you have some pen and paper or computer, do it, write something down, but to create a reward function. And I'm not going to give you much time. I just want you to kind of get a fresh intuition for this. But we got this simple grid world. Actions are up, down, left, right. And the agent's purpose is to reach the goal in the minimum mean time from any state. So I want you to design a reward function by designating what the reward should be from each action from each cell. I'm not necessarily recommending exhaustively writing each one, but express it in some way. It could be a constant for every action. But assume there's no discounting and the goal state is terminal in this task. So I'll just stay silent for like 20 or 30 seconds while you think about what reward function you might design. All right. Okay, so let's just go through some possibilities. Maybe one of these will be the one that you designed. So here's an aligned RL objective, and this is the one that most commonly you would see, and I think this is what you would see in the the Sutton and Bardo textbook. just a -1 reward every time step until you reach the goal. And one thing you can do to evaluate this is to then think about the return. So the return here is the time to goal times -1. And then from that, you can think about the expected return, which is the mean time, really the expected time, but mean time to goal times -1. And so then in plain English, you can say that the task is to minimize the mean time to the goal. And I'll come back to this in a later slide about legibility or interpretability of return. Here's a misaligned RL objective that might superficially seem reasonable, giving +1 reward for any action that moves towards the goal and 0 reward otherwise. I won't go through all the English below, the English description, but one question here is, will the agent actually terminate if it's acting optimally? And for this, the answer is actually no. So you're going to get some finite reward for getting to the goal, but an agent that simply goes in cycles where it makes progress and then regress over and over will get infinite return. So this is superficially seems reasonable, but will actually result in really undesirable behavior if you get to the optimal policy. So here's a more questionable one as far as whether you would consider misaligned or not. And it's 0 reward for any action that moves towards the goal and negative reward otherwise. So now we're just going to penalize actions that don't get you to the goal. And kind of skipping to the end, what this translates to is the task is minimizing the mean number of suboptimal actions, where I'm using suboptimal to refer to the original aligned task, but actions that don't move towards the goal. And so you might notice that the task definition includes having already solved the task. So on one hand, maybe you shouldn't do RL if you can define this reward function. But also, maybe you care about whether the goal has been moved, if the goal is moved, whether your reward function will still capture the task. So whether it generalizes. In this case, this is a very shaped reward, and it's not going to generalize to moving the goal. And then also you may care about whether suboptimal policies are ordered correctly. And that's our definition of alignment. Cares not just about the optimal set of policies, but the full ordering of policies. And in this case, it's not going to order, I believe, I'd have to think actually more about saying this, but I don't think it'll order the suboptimal policies by the amount of time that they get to the goal. Although actually that might be wrong. Anyway, so there's some considerations here where maybe you might consider it aligned, maybe you consider it misaligned, depending on how you plan on using the reward function. Okay, another point I'd like to make is that thinking about designing an aligned or problem side RL objective requires a change in perspective, or at least it's helped by a change in perspective. So the familiar perspective is taking that of an RL algorithm, where there's an agent and a learning algorithm that an agent is pursuing reward, and the algorithm is estimating expected return from the reward that it's experienced so far. And then the agent or learning algorithm is identifying actions, or more precisely changes in policy, that will increase its estimated expected return. So this is kind of the perspective of the agent that's trying to get better at getting accumulated reward. Alternatively, you can take a return-centric perspective of policies. And here, like we've talked about before, the choice of the reward function and discounting create an ordering over policies given a start state distribution via their expected returns and over full trajectories. So each change in the reward function or discounting can rearrange this ordering by changing each policy's expected return. And learning is not actually a consideration from this perspective about whether the problem specification is aligned with your preference ordering over policies or over trajectory distributions. And I may have forgotten to mention earlier that when I defined an aligned RL objective, I talked about rankings or preferences over distributions over trajectories, but because policies also create distributions over trajectories, that such an ordering implies an ordering over policies. And also by doing that, it defines the set of optimal policies. So this is new. This different perspective is thinking about the return and the expected return that your RL objective is creating and how that endorses certain policies over others or certain trajectories over others. Before I get into the next section, I just want to kind of put go on a slight tangent and make a pitch for erring on the side of legible or interpretable return. And so I want to look at two highly common reward functions here. We already actually looked at the first one, which is -1 reward until goal, and how you can change that to describe the task in terms of minimizing or maximizing some plain English phrase. Another one is maybe you're playing a game. We're just going to assume no ties for simplicity. And the reward function is 0 if you lose, 1 if you win, and 0 for all other moves, all other time steps. So the return here becomes a binary indicator of winning or losing. And the expected return becomes the probability of winning from whatever state you're in, given your policy. And then the task then can be said to be the maximize the probability of winning, which is very legible. I think most people would embrace this as a task specification. But you also might consider for some games, maybe entertainment or style matters in some way, or fair play matters in some way. And so then maybe this isn't a fully aligned objective, but it is a legible one and allows you to think about it more easily. Okay, now I'd like to get to this next section. And these are two methods for finding misalignment in a reward function. The first one, which is the one I recommend being part of anyone's tool belt, is to find mismatches in preference orderings. So if all human stakeholders agree that some trajectory tau A is preferable to tau B, which can be expressed here in this parenthetical, then for an aligned RL objective, then the return of tau of A should be greater than the return of tau B. So there's a simple test for alignment. And so we're gonna look at two of those trajectories we looked at before, tau idle and tau crash. Just to remind you, tau idle, there's no driving, but it's safe. In tau crash, you drive halfway and then have a crash. So let me just do a cartoonish illustration of how someone might get this misaligned. So the top one is tau idle, the bottom one is going to be tau crash. So it's getting some positive reward, the bottom one, for making progress, but then it crashes into the sheep and it gets a -1 penalty. So if we add these up, the return of tau crash is higher. And while this cartoonish example might seem obviously wrong, at a quick glance, what if instead it was a -1000 crash penalty? And like in autonomous driving, typically the time steps are 100 milliseconds. And so, then to get to 1000, 1000 of these +1 progress rewards, then you only need to go 1000 time steps, which is 100 seconds. So then you would basically be equating 100 seconds of progress with 1 crash. And so there's a version of this, what I've shown you, that again passes some people's like superficial sniff test, where the crash penalty is a lot bigger, but the time scale is also bigger. And so the same kind of mismatch happens where the tau crash ends up endorsed by the RL objective. In the work that I cited a couple slides before, we looked at published reward functions for autonomous driving. We reviewed 19 papers and exhaustively characterized 10 of them. Often details were left out, so we had to email the authors to fill things in. And I just want to give you one quick example to kind of get a little more intuition. On the far left here, this is one of the most legible reward functions that we saw. And that is for autonomous driving, the reward at a time step is the unweighted sum of 3 attributes: a time penalty at every step, a collision penalty of -10, and then a reward for reaching the goal of +1. And you might see that this might create the kind of mismatch issue that I talked about just before, in the sense that they're equating getting to the goal 10 times with 1 collision. So in the reward functions that we were able to estimate return for these two abstract trajectories, 7 out of the 9 of them incorrectly prefer the tau crash. And so, this is this is definitely problematic. Luckily, none of these reward functions are being used like on deployed autonomous vehicles. But I want to talk about this this method just from a slightly different perspective. So one way you can do this is, so you might ask, where do we get these trajectories? And the way that I would do it in practice is to kind of have some sort of baseline, typical desired behavior in mind as one trajectory, and then try to find trajectories that are undesirable, but your reward function endorses, that your RL objective more precisely endorses. So just try to be the person who, try to game this specification, do your own specification gaming, and find trajectories that are endorsed but are undesirable. Okay, so the second method for finding misalignment is to find undesired risk tolerance via indifference points. This is a little more complicated, but it's a little bit more powerful. So now we're going to bring back tau success. So we've got 3 trajectories, and the ordering of these is tau crash is worse than tau idle, and that's worse than tau, oh, sorry, this is a typo. Tau dest is for tau destination, but it's the same thing as tau success. So tau success is the best. So let's say there's a lottery and you can choose option A or option B. And option A is basically just tau idle. And option B is a probability between tau crash and tau success. And P is that probability that decides between those two. So this is actually pulling from expected utility theory. If there's such a relationship among 3 trajectories, and also if the return for those trajectories has the same ordering, so now we're only talking about 2 out of those 9 reward functions that actually has the correct ordering, then there's some probability P that balances these 2 options, where the return of tau B, or not driving in our case, is equal to the probability weighted return of possibly crashing and possibly succeeding. And this P is called an indifference point because from an expected value perspective, there's no difference between these 2 options. And so if you move P upwards, then it's going to be more likely to choose the left side, I believe. But basically, if you move it in one direction from the indifference point, then it's going to choose one option, and the other direction, it chooses the other option. So in this autonomous driving analysis, this running example that comes from this paper, for each reward function, we calculate P, and then we convert it to kilometers per collision, which is more human readable at this indifference point. So what did we find? First, some human reference points. Here's the safest group of human drivers, 50 to 60-year-olds in the US. And then here's the least safe, new drivers. And then here is my back of the envelope calculation for drunk US teenagers. And so what did we get from the reward function? So remember, there's 2 of them that allow this analysis. So their indifference points are here and here. And then also remember, 7 of them don't have indifference points because they don't have the right trajectory ordering. They just prefer the crash over not driving. So the most risk averse of these 9 reward functions still allows collisions at a rate of more than 4,000 times that of a drunk US teenager. Again, these are not, these reward functions are not training deployed autonomous vehicles, so there's not real immediate safety concerns. But it shows that the power of this technique to find misalignment. Another quick gotcha is that some algorithms have reward clipping, and so you may have a aligned RL objective, but because higher magnitude rewards are clipped, the RL algorithm may only see basically a different reward function that is not aligned. I also want to briefly talk about this well-known example here. So another gotcha is missing attributes. So basically, there are things that you care about and how you would order trajectories or distribution over trajectories that are not measured by the reward function. And this can cause what are called negative side effects. And this is a well-known example of what's called reward hacking. Accepting that for a moment, what appears to be wrong here is that the score is translated to reward. But when people see this example, they seem to be very ready to admit that this is bad behavior, even though nominally, and according to the specification, maximizing score is the task. And so it seems that there's something missing. So maybe because this is it's just a video game, but there's a narrative of a boat that's racing. And within that narrative, we don't want boats to crash, and we want racing to actually happen, not just have it spin around in circles. And so this potentially is an illustration of missing attributes. As I maybe hinted earlier, I'm not actually even sure this is an example of reward hacking, of like doing undesirable behavior that does actually get more expected return. I haven't actually played this game before, but my sense is that if you do this for a while, you don't get to go further and get more score. So my guess is that this is actually a problem of near-term rich reward, and that the RL algorithm is getting a lot of score in the near term, but not in the long term. But I'm not sure about that. My preferred example of reward hacking is from Ranlov and Alstrom from like 25 years ago, where they had a bicycle similarly looping in simulation to try to get progress reward over and over. All right, so let's get into the ways that misalignment commonly occurs. One is by shaping. So reward shaping, I'll define quickly. That's adding reward in addition to this true or environmental reward, which should be aligned, to aid learning. So giving hints or heuristics. And this looks like, so computer glitch there. So this looks like what I've got here on the screen. There's the true reward function R, and then there's a shaping reward function. They're added together, and the algorithm experiences typically only the sum, this shaped reward. Even though shaping research tends to assume separate reward functions, in practice, most RL problems only have one shaped reward function. They just put them all together, overloading the signal. So what do leaders in AI say? In the standard text on AI, Russell and Norvig write, as a general rule, it's better to design performance metrics according to what one actually wants to be achieved in the environment. So this signifies, this connects to the alignment definition, rather than according to how one thinks the agent should behave. And then in the standard RL text, Sutton and Bardo agree in almost the same phrasing, adding that imparting knowledge about effective behavior is done better via the initial policy or initial value function, or influences on them. I left that out on the slide. So a simplified version of what they're saying is specify how to measure outcomes, not how to achieve them. And you could interpret that as saying not to shape rewards. I'm not going that far to say you shouldn't shape it. So there are various types of safe reward shaping methods. The best known is potential-based reward shaping. I'll just quickly highlight a little bit of this. The assumptions are often overlooked in this paper. It's not safe in all contexts. And I should say safe means that the set of optimal policies won't be changed, or sometimes it's the ordering over policies. And I also want to highlight that Wiwora et al. I have the wrong years on those. I think it's 2003. Wiwora et al. Showed that a version of potential-based shaping is equivalent in the tabular setting to just initializing the Q function to the potential function. And my suspicion is that this is part of what informs the statement in Sutton and Bardo that initialization is a better place to impart knowledge. Okay. Going back to these autonomous driving papers, we found 13 out of 19 include reward shaping. Here are some examples. I'll just read one of them of encouraged behavior. One of them was staying close to the center of the lane. So again, we exhaustively characterized some of those papers, and of the 8 that had reward shaping, none of them described the separation of their shaping rewards and their true rewards. Presumably there was no separation. None of them used a recognized method of safe reward shaping or discussed the safety of reward shaping. 2 of them acknowledged that they did reward shaping, and only 1 of them talked about potential adverse effects. So while there's literature on shaping that looks at it very rigorously, the way it's being done in practice looks quite different than what the literature talks about. So the recommendation for shaping here that I'm going to make is to create an aligned reward function without shaping, and then optionally add a shaping reward function. There's other ways to impart knowledge, but this is one way you might do that. Why? So one is clarity. These are 2 sources of information. The aligned reward function, aligned RL objective, is meant to communicate the task, and the shaping rewards are giving policy guidance, and sometimes change the problem specification. So they're 2 separate sources of information. Presumably you can think better about them if you do them one at a time and not all together. And then also having them separate helps with debugging. So for instance, you can do a sort of an overfit plot where, so here we're plotting the true return and the shaped return. And you might see your RL algorithm over training get higher and higher shaped return. But if you're plotting the true return too, you might notice that it plateaus or even goes down. And what that tells you is the problem is not with the RL algorithm, but rather it's a mismatch between the shaped return and the true return, where getting more shaped return is not translating to better performance. All right, so another form of misalignment is by trial and error design. I'm going to go quickly through this one. I'll probably skip some of it. So imagine you want to design a new RL objective. A trial and error way to do that is you train your RL agent using the candidate objective. You observe the behavior, the learned behavior during and after training. And then if you're not happy, you tweak the reward function, maybe the discounting, maybe tweak the RL algorithm too, and then repeat. And you just keep cycling until you're happy. So you're effectively being a human optimization algorithm. This has been called graduate student descent in broader context. And you're fitting your RL objective in part to your training setting, including your RL algorithm. This is the norm. In 2 different analyses, we found 100% of reward functions were created by trial and error, and then in another 92% were. And so one of the big questions and potential problems is this overfitting question. So are you overfitting the RL objective to the RL algorithm, its hyperparameters, how long you're training it, or maybe the version of the task that you're running it on? So again, you can kind of end up seeing this like overfit plot, but this is a different kind of overfitting, where if you change the context, you might find that your RL objective doesn't do well anymore. The question here is, do we find this in practice? The spoiler is yes. We look at the hungry thirsty domain. I'm going to just jump ahead a little bit. But basically the gist is we had RL experts come and do reward functions, and we found overfitting frequently. And then I think this is worth highlighting. So most experts used a myopic design strategy where reward was ranking different groups of states by their desirability. And I won't go into the details here, but the flip side of this is that by just ranking states by their desirability, they didn't seem to be thinking about how these rewards would accumulate to make return. And so they might be endorsing staying in worse states that are more frequent, because those smaller rewards for the worst states still add up to a higher return. And so the agent never seeks these like better states. And so one provocative question here is whether possibly the word reward could be harming reward design, because reward colloquially doesn't have a strong connotation of being additive. You have to really train as an RL practitioner to really get that deep intuition that reward is a thing that's being added to make return. Whereas, maybe cost or score would have a stronger connotation of being additive and make people think a little bit more about its accumulation. So takeaways are that overfitting can happen with this trial and error design, which is very prevalent, and that RL experts do appear to do so in practice. One of the important consequences of this is on algorithmic comparison in research, including ablation studies. So if you tune your RL objective to your novel algorithm, and then you compare your algorithm against some state-of-the-art algorithm and show that yours is better, that is an unfair comparison because you likely have overfit your RL objective to your own algorithm. Likewise, if you do an ablation study and you've tuned to your full algorithm, that's also unfair to the ablated versions of your algorithm. And so you may be getting scientifically invalid results. Okay, another one is misalignment by discounting. I think for time, yeah, I'll just talk about half of this, I think. So bringing back in discounting, exponential discounting is not the only way to do it, but that's what I'll focus on here. The main thing I think that's most important when creating an aligned RL objective is to consider the discount factor as a part of the expressivity of G. Basically, G is the way of assigning return to a trajectory. And given that there's a definition of alignment is that G should create orderings over trajectories and distributions over trajectories that match human orderings, then essentially you can consider the discount factor, or whatever discounting you use, to be a form of expressivity to express that preference ordering through G. Here's exponential discounting. All this is meant to show is that after some amount of time, the impact of reward becomes basically negligible. In practice, there are often two discount factors, and this is often ignored. There's the problem side one that I'm arguing should be aligned, and that's part of the problem definition and creates this true return. And then there's the algorithmic discount factor that is a feature of the deep RL era. And usually it's smaller than the problem side one. And typically it's less than or equal to 0.99. And so the recommendation here is don't confuse them. And if you're doing that kind of first overfitting plot of the true return versus the shaped return, one of them, the problem side one will go in the true return, and the algorithmic side one would go in the shaped return. This is something that's in the paper, but there's a technique for getting an intuition about how severely your discounting is reducing the value of future rewards. And so if you're asking why your RL algorithm is not seeking certain things that are positively rewarded, this can be a technique to assess that. Okay. Designing aligned rewards. And now we're getting to the positive part, where instead of just saying all the things that can go wrong, I'm going to try, this is maybe more difficult, try to propose an improvement. So I will propose, I'll try to make it a good proposal. Okay, so there's no best practices for creating aligned reward functions, not yet. But here's a sketch of a possible best practice. So there's 4 steps here. So the first one is to consider the simplest set of outcome variables that differentiate varying levels of success versus failure. So, one outcome variable might be the time it takes to the goal. And then, thinking about soccer as a task category, you might have whether you win or not as your outcome variable. You might later decide to shape by rewarding a score, but really in the end you could score 100 goals, but if the other team scores 101, then I think the score can be very misleading, or your own score. So whether you win or not seems to be important, but you also again might consider things around entertainment, other things that are important in terms of your preference ordering. And then try to find a per time step version of each of these outcome variables so that when you add up this per time step version over a full trajectory, it adds up to its full trajectory value. So for time to goal, that would be a time penalty, some constant time penalty at every time step. Okay, so the second part here is to create a parameterized reward function representation with these variables. And my recommendation, this is all a sketch, it needs to be validated, but my recommendation is to try a linear representation and then stubbornly try to make it work and move to nonlinear only if you really can't accomplish step 3 here. So step 3 is to tune the parameters of your reward function representation so that its preference ordering over outcome distributions matches yours. Yeah, I actually should say, I've been saying reward function in here, but this includes the discounting. So it's reward and discounting. And then the last one is evaluate. That's only one word, and it's somewhat hand-wavy because it's actually a difficult question to think about how to evaluate an evaluation metric. In the end, an aligned RL objective is one that expresses your preference ordering, and that's already incorporated in step 3. And so there's a difficult question here about how you decide that you've actually done a good job. And that's something we could talk about given I think there'll be some time for questions. And you can go back to earlier steps if you learn something, but importantly, you shouldn't be tuning to make an RL algorithm perform better. You should only go back based on insights about the alignment of your RL objective. I just want to note that step 3 here is very closely related to RLHF. You're using preferences to tune an RL objective. In practice, there may be some ways where it technically is RLHF, but it looks somewhat different than the most common types of RLHF. So to summarize, I talked about catching, so various tools and insights were presented. I talked about ways to catch misalignment by looking at preference mismatch. And you can look at trajectories directly for 2 trajectories or trajectory lotteries, finding indifference points. There was content around shaping, and I advise to keep a separate shaping reward function if you're going to shape, to plot the true return versus the shaped return to detect overfitting. And then also to consider a shaping method that does not change the preference ordering over policies or outcome distributions. So what I call a safe shaping method. Under the category of trial and error reward design or objective design, the main takeaway here is that, besides that it's common, is not to tune your true RL objective, your aligned one, to directly improve your RL algorithm's performance. Save that for kind of solution side, trying to tune your algorithm. Under discounting, I recommended keeping a separate problem side discounting scheme, gamma if you're doing exponential discounting, and then briefly mention that you can calculate the time until your reward is discounted to 10% of its original value, or 1% or 0.1%. And then also I mentioned consider clipping and whether that's practically causing misalignment. And then also bias your design towards having more legible return and expected return. So just for future work, to mention a few things that I think would be really helpful. One is to validate and refine best practices. So I sketched one possible set of best practices, but we don't have a validated set. And I think this is a big hole in the field of RL. Another one is sometimes the reward can't be practically aligned, or the RL objective can't be. So perhaps maybe some outcomes that matter just can't be measured by the learning system. And so thinking about what to do in those situations would be impactful. And then I talked a lot about some debug methods for creating an aligned RL objective, but there aren't necessarily tools right now that are readily available to make that really easy to do. So I think one of the biggest reasons that some of these recommendations aren't adopted is that they're extra work. But I think that often people end up in sort of a local maximum, and that I do think a lot of these methods are worthwhile. And all of this also could be cast in a AI safety agenda where, for high impact AI applications, the misalignment of an RL objective could cause problems, that could be cast as dangerous. And so in studying this topic, ideally, we could fix those problems that cause misalignment, but also there might be some categories where RL shouldn't be used from a safety perspective. But right now, I don't think we have precision on those questions. Second to last slide here, I do reward design consultations for academics and nonprofits. So if you are designing a reward function and you just want to talk to someone who thinks a lot about reward, I'd be happy to talk with you. And then I will close just by mentioning that these are the 2 past papers on reward design that I pulled a lot of content from. And the paper that corresponds to this talk can be found by this QR code. So thank you very much for listening, and happy to take questions.
First, so Ryan, excellent talk. Thank you very much. Lots of things that resonate with things I'm thinking about these days, even though I'm not looking at RL, looking at the simple decisions. I guess my question is, it sort of sounds like you're saying we should be matching what people do. And I keep wondering, aren't there exogenous things that, again, you're playing a game and you want to win the game, done. Aren't there situations where there really is something which isn't what a person does, but what a person should be doing? Can you comment on that?
Yeah, great question. So I think when you get preferences or design an RL objective, there's tension, which I think popped up here and there in the talk, between specifying or giving preferences over what behaviors you want versus what outcomes you want.
Yes.
And one of the themes of this talk is that, at least for this initial step of creating your aligned RL objective, you should try to avoid hints, try to avoid things like what you said, like what humans do, but rather you want to understand what outcomes people value and in what ordering. And then if there's stochasticity in the environment, you also want to ask what distributions over outcomes are valued over other ones.
I got to follow up, but let me let other people ask questions.
So you mentioned a reward function where the crash trajectory was better than the ideal trajectory. I understand that okay, makes sense. This reward function is obviously not good. Then you mentioned the second example where even though ideal trajectory is better than crash trajectory, since RL algorithms maximize the expected reward, you can get a policy where this ordering might change under expectation, right? While answering Russ's question, you also mentioned about thinking of distributions. So my question is, sure, we can manipulate rewards, and then we can get a behavior so that we can get a situation where if you maximize expected rewards, you'll get very good behavior or desirable behavior. But what if we think about, instead of maximizing expected reward, I don't know, maybe we think about finding better distributions over rewards, some kind of stochastic dominance, or we think about, what if with high probability my policy gets a better reward than the other policy? And does that make sense?
I'm not sure I totally followed that. So the proposal is to specify your problem so that you're able to choose policies based on their distributions over reward. I'm assuming you mean distributions over return. And then that means, there's different ways you could evaluate a distribution over return, but the normal way would be to take its expectation. And so then I think we're back in the same paradigm that I'm talking about. Unless you're recommending like a different way of handling those distributions.
Right, as opposed to changing the reward function. But anyway,
I see. So you're not maximum. So this would be like things like conditional value at risk, where you might, take the expected return of the bottom 10% of of situation, or the return of the bottom 10% of the distribution, and try to maximize that. So my understanding, I'm not sure how well I could articulate this, like, on the spot, but my understanding is that things like that are more or less band-aids on a misaligned RL objective in the first place. That if your RL objective expresses your preferences, including your preferences over distributions of trajectories, then you are actually misaligning your objective to do something different, including C-bar. Rich, you have a question?
See, Rich Sutton has a question online. Rich, you want to unmute and ask us?
Yes. Excuse me. Brad, thanks for the talk. So very interesting stuff. One of your goals was to not include how a designer might try to help the agent by giving hints.
Mhm.
And I think it was your goal not to include that. And so you didn't include, for example, initializing the value function to to something that would help the agent get to a good result. But then later in the talk, you talked about potential-based shaping, and you did include potential-based shaping, and I think you included in your best practices. But we know potential-based shaping is formally equivalent to picking an initial value function equal to the potential function. And so I think you did include, in a sort of a backhanded and limited way, setting the initial value function. And so it seems to me like you should either embrace that or exclude it. You got to make up your mind.
I appreciate that. So yeah, I think that's a good point. So so just to be clear, I'm not saying don't do these things. Don't shape. I'm saying to save it for after creating your aligned RL objective. And so maybe it's semantics to say that potential-based shaping is on the algorithmic or solution side, not on the problem specification side. I think that's the stance I'm taking, and I think you're also probably picking up on me not always marking when I'm moving from, like, we're talking about aligned RL objectives, but then here's some practical considerations as you also are crafting your solution. And so I think I could probably delineate those a little bit better. But all that said, there's still a question of let's say it's a time to goal task, like it's a grid world, you want to get to the goal. And so a simple aligned reward function, like I said, would be a time step penalty of -1. But you also could have a reward function that is the result of potential-based shaping. And so one way that I'm advocating against that is the legibility part. So that would be a more complex reward function, and because of that, it would be harder for a person to like eyeball it and really grok what it represents and how well it aligns to their what they're really trying to express in the task.
Brad, a little follow-up. Do you believe that potential-based shaping is part of the objective design? And does potential-based shaping change the ordering over policies?
Not under the assumptions in ING at all.
It does not.
Right.
So it's not part of that subject.
Yes. So the legibility part is separate. It's part of the assessing the alignment. So the simpler and the more legible your reward function is, the argument here is that the easier it will be to assess whether it is aligned.
Okay, thank you.
Yeah, so Brad, I really like the fact that you were talking about utility functions on trajectories and preferences on trajectories. But then you kind of started saying implicitly that the utility of a trajectory has to come from adding up a bunch of rewards over time, right? And that is coming from the NDP formalism. And a lot of the problems you were pointing out seem to arise from the fact that people have in their heads a way of preferring trajectories. It's really hard to translate that into like a sum of rewards over time, right? So I was wondering like if part of this problem is coming because we are trying to like fit ourselves into this MDP box that demands that our preferences over trajectories come from adding up rewards. But for example, if you had something like constrained MDPs, then you could directly say that I want a car that gets to the destination as fast as possible while simultaneously not crashing, right? Rather than trying to like come up with like one scalar reward that combines both of these objectives, you could just give it a constraint and a reward to maximize subject to that constraint, right? So I wonder like if you think that switching to something like the CMDP, which allows you to come up with other preferences over trajectories, might solve some of these problems.
So because of the audio, I couldn't hear everything you said, but I can address the last thing. So I'm not an expert on constrained MDPs, but my understanding is that these constraints are not telling you how to trade off violating the constraints with with your other objectives, the other attributes of your reward function, or with the attributes of your reward function. So for instance, in autonomous driving, if you just tell the car don't crash, that doesn't really tell it how to act in the face of risk. And the expected utility theory framework allows you to incorporate assessments of risk and like different tolerances of risk in the utility function, which here maps to the RL objective. Did I address? I apologize if I didn't hear your question right.
Yeah, so I guess what I was trying to say is that expected utility is like a very particular expected utility as a sum of rewards is a very particular kind of objective, right? And so constraints allow you to broaden that set of like you can say more things with constraint functions than you can say with one scalar reward function. So like why limit ourselves to scalar reward functions and then like suffer all these problems when you can give yourself a more expressive vocabulary to talk about risk and yeah, balancing different trade-offs and so on.
Okay, that's a good question. So this may be hitting a limit of my understanding of constrained MDPs. Maybe I misunderstood that they have hard constraints. If they are actually more expressive than just giving a reward function, then I don't see how they would be harmful from an alignment perspective. But if like you're giving a hard constraint and that actually makes them less expressive, then that may limit your ability to express people's preferences over trajectory orderings and distributions over trajectories.
Let me comment. It's 1 o'clock now. People who want to leave are welcome to. Those of us who have more questions are welcome to stay around. I assume it's okay with you, Brad.
Yeah, I can stick around for a little while.
So I have several more questions. I know Osmar has a question, and I see Don also has a question. Osmar?
Oh yeah, in the example you gave with the case of idling or going and risking a crash, you have probability P, and it seems that you assume that P is fixed during the trajectory, but P may change, and in that case, the misalignment can continuously change. What happens in that case when your misalignment is not fixed? It changes all the time.
That's a good question. So the trajectory. So we're comparing two trajectories in this the simplified, but still can be real world example. And so you might say that the probability through the trajectory of collision changes. But if we're saying that there's two trajectories and there's a probability of crashing, or one of them is crashing, then I guess I'm having trouble following the question. It's not that like you've got some system moving through a task and you're assessing risk of collision at any point, but rather that in this like abstract scenario, there are these two trajectories, and you can turn it into, you can convert it to a more real world scenario where you might say, I have a fixed policy for my autonomous vehicle, and I have this like meta policy that's deciding, given that there's a storm outside, do I drive or not drive? And so then you have this kind of the same thing, but in a more complex way. But it kind of boils down to the same thing, that not driving is option A, and option B, there's a number of different outcomes. The main two outcomes to consider, I think, are that the drive in the storm is successful, or that the drive in the storm results in something negative, like a collision. And so I do think, even though the version I gave was very simple and abstract, I think it can translate to real world analysis as well.
We have Gautam has a question on mute.
Oh, yeah, thank you. Yeah, thank you for the talk. It was really interesting. So I have been thinking about reward design and task specification in reinforcement learning, especially in the context of robots.
Mm-hmm.
So one of the reasons we do reward function design is we try to craft a dense reward, which is informative for the agent. And part of the reason we do that is because it helps us with better exploration for the agent, and then it also learns fast. So if you have a sparse reward, I think the problem of alignment more or less goes away, because there's just one thing that you recognize as the right thing. But then you have the other problem, which is if you have a sparse reward, exploration is now an issue. And then there's a chance that the agent doesn't learn anything useful, right? So my question is, what is your take on just maybe, let's say we stick with sparse rewards, so this way we handle the alignment problem, and then we solve the problem of exploration instead.
Yeah, so I think what you're saying, I guess two things. One, in talking to people, I feel like it's the roboticists who are doing the most RL objective design. It seems that most other people are typically working with existing benchmarks, and roboticists are always running into like new problems, and they need to craft RL objectives for them. And so I think it's particularly relevant to this talk to bring up robots. But I think what you're saying is compatible, that yes, the sparse reward function may not help with exploration, but it gives you that alignment signal. And, I'll just say, like, one thing that I didn't mention is that I have, when I like think about these things, I'm thinking about current algorithms, but also, a vision of future algorithms. And in my mind, the idea that giving an aligned but maybe difficult to learn from evaluation metric to your learning algorithm should help. Like, there should be some way that it can use that information as a separate type of information. And so even though maybe some existing algorithms wouldn't be able to use that, it's still, I think it's still valuable, especially in terms of long-term vision of RL. And then I'll just say, like, this shaping reward, I'm actually very curious about why people choose shaping reward. And I have like some speculation, because there's a lot of other options. Like you could do a warm start with demonstrations. And in some ways it's easier to think about how to demonstrate than to craft this numeric function that gives hints and may accumulate in weird ways that you don't expect. And and you could also, there's ways to learn policies directly from preferences, or bias policy learning from preferences. But yeah, I'm kind of curious about why shaping rewards seem to be the default. And I sort of speculate that it's a ease of coding, that basically you've already got your reward function, and then it's like a couple extra lines maybe to add some shaping reward. And that's also why it ends up just being one function instead of two separate ones. Whereas learning from demonstrations requires a different data pipeline and an additional algorithm. Did I address your question?
Yeah, thank you.
Great.
This is Russ again. Let me return to the question I asked earlier. So my context is not reinforcement learning. It's just simple supervised learning tasks. I work with many medical doctors, and have many interesting questions that come up in that context. Often they have to make decisions about, do I give this medication or that medication? and which one's better, and or would I use this procedure to decide what to do next? And they use things like AUC, which is a really stupid measure to try to get some sense of it. And my comment is, if I follow this particular procedure, there's a certain chance of a false positive. What's the cost of a false positive? If I follow this procedure, there's false negatives, so a false positive could be, I said this woman has breast cancer. They now do an expensive, complicated biopsy with some risk, but it really wasn't necessary. A false negative says the woman's fine, go home, and she dies, a year later of breast cancer that could have been cured. So look at the consequences of the actions that are taken, false positives, false negatives. And I've been trying to advocate, just as you were saying, what are the consequences? What is the cost? Try to give me some exogenous measure that says, every unnecessary death is the same as 35 different procedures that are followed, or something like that. But of course, I've talked to hundreds of doctors, and no one can articulate that. They say, well, here's what I would do. I would do this here. And I don't want to follow what they do. I'm hoping that there's a way to get them to actually say, here's the actual cost function I really care about. And now it's not a matter of the doctor's preferences. The preferences are in terms of articulating this false positive, false negative trade-off, not the actions that they took. Does that make sense?
It totally makes sense. And I think it's a practical dilemma for doing this kind of stuff. I think often the stakeholders will push back on something like this. And I'm pulling from anecdotes. So for instance, somebody was telling me about trying to better, I'm trying to remember, they were trying to come up with like a single evaluation metric for like a recommender system for like a major company. And the executives who like could green light it, they were unwilling to just craft an evaluation metric that didn't reflect that nothing should go down. Like none of the individual components that they measure should go down, which is like probably like a political consideration that if anything goes down, then they can like get pointed at, even if like in their sense the system's performance overall went up. So yeah, I think just generally that's a challenge. I don't have like an answer for like that like practical issue, and it also might be that we're wrong. Like we more mathematical people could be somehow missing something about the practicality of it. But yeah, I totally agree. Like I was involved in brainstorming for like an organ transplant advising project, for whether you take a available organ or not, and we talked a lot about like what are the consequences of the transplant, and looking in the literature, there's a lot of like kind of near term signals that people use to make the decision, and the studies follow up with some longer term signals. But I think there's also some challenge related to like measurability, and often the further, the more fundamental the outcome you're measuring, like quality of life over the next 10 years, the more there might be other factors that influence it. So there's more variance and just other difficulties for using it. So I think that's an open question of how to use these types of evaluation metrics that are aligned in these more practical scenarios, maybe with very long-term consequences. And I know other fields have looked at this outside of RL in a lot more detail.
Again, one of the criteria is to not just be actionable decisions, the consequences, but have objective measures, which is another big complication in these areas. But I can spend another 20 minutes, but I won't have. Other questions?
So I can take one more question. I've got a meeting coming up.
I had a question about this whole design, like say pertaining to autonomous driving, where you basically have partial observability. So you have trajectory of observations, and while you're designing your reward function, you're making some assumption on what your state is, right? And how does that play a part in the design process? Because you could have you might not have crashed yourself, but you caused a crash like 5 seconds earlier between two other people. And so that depends on what you assigned your state as, which depends on what you could observe. But even with what you could observe, you're assuming that there's a Markov reward with some particular state assumption, right?
Yeah, I really like that question. It's something I've thought about some. I wish I could give like a conclusive answer. But yeah, so if the reward itself is partially observable, then if you still have the observations needed to have a effective policy, then it may be that you're able to like model that reward as a consequence of those observations. And I've wanted to like look at that theoretically for a little while. It also might be the case that if you really don't have a good path to being able to measure things, like if you caused a collision that's out of sight, then that might be a reason to favor like a non-RL method, like imitation learning or something like that, where you have these experts who aren't perfect, but they're above societal's level of performance, threshold for acceptable performance, and they're able to drive well enough, and so you learn directly from that. So I think this is part of the considerations of when you're trying to craft your RL objective. If you really can't get that aligned, that might be the point where you say maybe RL is not actually the approach that we should be taking.
Well, thank you very much.
Yeah, thank you all. I really appreciated sharing this work in the discussion afterwards.
I'll send you an email about some other ideas. Thank you.
That sounds great. Yeah, I'd love to take any questions or follow up.